Have you ever wondered about the conditions under which a car can perform the loop-the-loop trick, as opposed to the conditions under which it fails? So in this video, we're going to come up with a way of describing these conditions. So it all comes down to what's happening to the car at the very top of the loop. Now at the very top of the loop, there's a couple of forces acting on the car. We've got the weight force, which makes the car fall, and it's given by mg. We've also got the normal reaction force from the track pushing down on the car. So at the top, the net force is equal to the weight force plus the normal force. Now this track is circular, so the car's going around in a circle, and we've seen that the acceleration when something is undergoing circular motion is given by v squared on r. So the net force acting on the car as it traverses this circle is given by mv squared on r. So we know two things. We know that the net force pulling the car downwards is given by mg plus n, and that this net force must be equal to mv squared on r as it's traversing a circle. Now for the borderline case where the car's just about to lose contact, that will happen when the normal force from the track on the car is equal to 0. So if the normal force is 0, then the net force acting on the car is just the weight force mg. So we've got the case that mg is equal to mv squared on r. So we can use this to come up with an expression for the speed the car needs to have at the very top of the loop in order to traverse it. So we've got mg is equal to mv squared on r, which tells us that g is equal to v squared on r. So v squared is equal to rg, and v is equal to the square root of rg. So if a car speed is greater than this at the very top, then it will make its way all around the circle. Now, as we'll see in the next topic, the speed of the car at the very top is actually slightly different to the speed of the car at the very bottom as it's entering the loop. But if the radius of the loop isn't very large and it's got quite a high speed coming in, then there's not too much difference between these two velocities. Let's check this equation now with tracker. So here's the car being released from the higher point in tracker, and we can read off the speed of the car at the top here. It is around about 1.108 meters per second. So that is higher than 1.05, which is why it was able to make it around the loop in that case. Now let's have a look at what happens when we released it from the lower height. So here's the car being released from the lower height, and you can see that the speed is much smaller. So around about when it started going, when it was about to change direction, the speed was only 0.403, and so it didn't have enough speed to make it around the loop in this case.